Students, let's continue our lecture number 2. This is going to be a series 2, the complete one. Now we will move to the thermal analysis in terms of you want to transfer heat from inner system to outer system, because as you know that the failure rate depends strongly on your junction temperature. Let's start with the steady state heat transfer by conduction. In the nature, you know that the form of the heat transfer mainly are two types. The first one is conduction. You transfer the heat by some kind of medias in terms of solids. For example, you have coppers, you have glass, etc. The second one is the convection. You transfer the heat by some kind of medias, for example, of fluids such as water, such as air. You turn on the fan, right? So you feel more comfortable. It's cooling you down. And the last one, you don't does not require the meteors. That's the radiation. You can see that the sun can transfer heat from the sun to the earth through a vacuum ring. That's not, you don't have anything, so you have no meteor. That's the radiation. Now since you are electronic engineer, we will compare electrical circuit and thermal circuit for the simplicity, as you already have background in electrical circuit. That's not much different, but you can say that's very similar. For electrical circuit, you have a electrical resistor. By applying Ohm's law, you know that if you have the voltage different between resistor, the current will flow, and your resistor actually, by the name, that resist the flowing of the current. So that's your delta V equal to IR, where delta V is the potential difference in the unit of volt, I is the current in the unit of amps, and R is the electrical resistance in the unit of ohms. And they both are in the term of in series and parallel. For the thermal resistance, you have a temperature difference across your thermal resistor, and you have a heat transfer from the higher temperature T2 to the lower one, that's T1, and your RT is the actually resist or limit the current, the heat in the term of watt through the thermal resistor. And you have our thermal equation, delta T, or T2 minus T1, that's equal to QRT. From this equation, you know that RT as the unit of degree Celsius per watt, because the delta T as the unit delta 0 degree Celsius, and Q is the unit of watt. So RT simply as the unit of degree Celsius per watt. You also have a thermal resistor in series and in parallel. It's working as the same as the electrical circuit. For electrical circuit, you know that if our resistor connected in series, you have the same current flowing through your resistor, same as the thermal resistor circuit. If they are in series, you have the heat Q transfer through each resistor, the same or equal heat, and our total simply become RT1 plus RT2 plus 2 RTN. For a parallel electrical circuit, you know that when you have an incoming current, and then we will break into I1, I2, and I3. It depends, what is the R1, R2, and Rn. For the thermal circuit in parallel, you also have the Q1 flowing transfer through RT1 resistor, RT2 resistor, and RTN resistor. And our total working out the same way as the electrical circuit. So I is the equivalent to Q, or the current equivalent to the heat transfer, and the voltage is the equivalent to the temperature, and your resistor, electrical resistor equivalent to the thermal resistor, RT. As you know, your R equal to rho L over A, where rho is the resistivity, right? And L is the length along the path, that's the current flow, and A is simply the cross section area. For thermal resistance, still very similar to electrical resistivity, resistance. You have RT equal to L over Ka, where K is the thermal conductivity in the unit of watt per meter degree Celsius, according to table 8.3, page 316, in my book. Take a look at the one-dimension heat transfer. Just to get a better idea, and your thermal resistor are in series, and you have our external system, and on the most left is the inner system. You have the ambient temperature 25 degrees Celsius, and you have Tj, that's the outermost junction temperature. You're looking for the junction temperature Tj12, Tj1, J23. The heat will flow from the higher temperature to the lower one. Now you start with the RT3, since you already know the ambient temperature or the external temperature or the room temperature, that's the 25 degrees Celsius. Since they're all resistor connected in series, so you have the heat flowing throughout from the left to the right, the same heat, or in the term of watt. You set our equation delta T equal to QRT, or Tj3 minus T0, that's equal to QRT3. You can work out, for T23. You can see that you end up with 325 degrees Celsius. That's much higher than the ambient temperature which is the 25 degrees Celsius. So that's one kind of you have to be careful about design your system just to optimize your junction temperature. You don't want your internal system have too high temperature, otherwise it's going to affect the performance of your system. The rest you can work out and find the junction temperature TJ12 and TJ. Now for the system in parallel, you can work on we are looking for the internal system temperature. So when you have a RT1 in parallel with RT2, you're looking for RT total, and that in that case you can find the internal temperature T. You already know the ambient temperature or room temperature, that's 25 degrees Celsius. Your T ends up to be 91.7 degrees Celsius. You start from external temperature or room temperature, that's 25 degrees Celsius. And after that, you can look for the heat flowing through thermal resistor RT1, that's Q1, and Q2. You work out the same as you're working on your electrical circuit. By applying delta T equal to Q1 RT1, that's your Q1, 6.67 watt, and your Q2, that's the 3.34 watt. If you take a look at the RT1 and RT2, you can see that RT2 is double of RT1, rate 20 and 10 degrees Celsius per watt. So the more T, the lower Q will be able to transfer through that resistor. And you can see that since the RT2 is higher than RT1, you have less heat transfer through resistor. For the higher resistor, for the higher resistance of RT2, you have a lower heat transfer through RT2, that's 3.34, and this one is the heat transfer through RT1, that's double, right? Multiply 2 by 3.34, that's end up with 6.67 watt. That's work out the same as electrical circuit. Okay, I will wrap up with the thermal resistance network for dual light package, or DIP for the short, or PTH, pin through hole. Dual is mean 2. This means your package have 2 rows of your pins or leads. And PTH, by the name, you have to drill your PCB or printed circuit board to do soldering to mount your package or your IC. That's how comes the name PTH, pin through hole. You also have the surface mount. You have a leadless package, etc. This is a typical structure of your package. DIP package, 16 pins. You have your device on silicon chip or your wafer, and you mount that chip on the frame by you take the bond, and then you have leads or pins. In this case you have 16 pins. The first thing to start, because we want to analyze the thermal transfer in your package, you need to draw your thermal resistance network by the principle that the heat will flow from the higher temperature to the lower one. So your heat that's generated by your device in the term of a transistor, in the term of a resistor, etc. So that heat will flow from the top to the bottom, and that's why you have your thermal resistor in series. You have RTS, that's the source heat. RTSI, that's from silicon chip, right? The chip made by silicon. TE is the you take the bond, and then you mount your silicon chip on your lead frame. That's the copper or any kind of like electrical conduction materials. And then you molded your package with plastic. That's why you have your RTP, just to prevent your chip from humidity. And then you have RT, from your pins or package in parallel, 16 pins. So the heat start flowing, starting transfer from the top to the bottom, and then we go through 16 pins of your IC package, and you can analyze the junction temperature. For this case, I brought this down as the TS SI. That's mean the junction temperature between the source and the silicon chip. TSIE, that's from the silicon chip, the junction temperature of a silicon chip, and you take the bond. Okay, I'm going to left this third topic, and viewer continue to my lecture number 3 later on.